Okay, cool. Recording is on.
All right, so we can go through the chapter kind of in order, but let's just open it up and see if anybody had any specific questions, or doesn't have to necessarily be a question, but something you wanted to talk about.
I think one thing to start is how many of you have had the experience of training a model before? Because I think they kind of jumped in directly on the features, and I think it would be interesting to hear how many of you have gone through sklearn and trained a model on features before, so you at least have that basis. I want to know kind of generally where are you guys starting from?
Do you want us to reply in chat? You want us to shout out? How do you want us to reply?
Yeah. Yeah, it's a little hard to do this virtually.
You can just shout out. That's fine.
Well, people are in the chat are marking answers yes and no, things like that. That might be easier to visually see.
Yeah.
Yeah, on the participant list, you can do the yes, no.
All right. I see some yeses, some nos.
Okay, looks like decent number of yeses. So for me, I've worked with this stuff a decent amount, but I think that from my perspective, at least, if I was just jumping in and I hadn't trained a model before, I think that this would be a little bit overwhelming because they started immediately with scalars, vectors, and spaces, and they didn't really talk very much about how that relates to models. Like they didn't show, oh, maybe you can draw a line through these points in order to separate them or anything like that. So at least for me, I think I would have started the book a little bit differently so you could understand how the features might interact with a model or something like that. So they talk about the scalar vector spaces. And so the general idea there is, imagine you've got a set of features. You've got, let's say you're trying to predict house prices or something like that, and you know the number of bedrooms, and you know the number of bathrooms, you know the square footage, you know that everything else about the house. And then you can build a model, maybe a simple linear regression or something like that. You might have learned that in something similar in high school or college if you took a stats course. And so you can take those features and then you can build essentially a line that is trying to fit properly to the data. And so that's all you really need to understand there. The specifics of scalars, vectors, and spaces is not that important. You just need to know that you're taking in a list of numbers and you're trying to do some mathematical operation. And then your output is trying to be the house price or whether or not they're going to buy something or not. There's lots of different examples there.
And it's really helpful if you just imagine it as the coefficient of a polynomial or the coefficient of a term. So you're just multiplying it by some number that you're trying to learn. You're trying to learn what number you need to multiply that feature by. So how many square foot equals how many dollars of price, for instance, an example.
Mm-hmm.
And then and then your model is just trying to see what that number is, and it's trying to do that for all your features.
So I mean, they kind of went over two types of transformation, which were scaling and then the power transformations. And they mentioned specifically that with scaling, that's something that you want to do before you feed into models that are, you know, that will vary because of the type of scaling that you're doing. But has anyone done any power transformations before putting it into a model? I thought that was more of like a visualization aspect. but I'm not sure.
Oh, no, definitely. It's so if you ever see any curvature in your residuals plot, take each of your features and plot the error, and you see anything other than white noise, then that's an opportunity for you to do some sort of transformation. And if it's curved like a U, then you square it. If it's curved like an S, then you cube it. If it tails off at high numbers, then you log it. If it goes exponential at high numbers, then you exp it. So there's definitely, yeah. The transformations help a lot, and what they do is, but you're doing it manually, and I'm sure they'll get to this later in the book, but of course deep learning takes care of that all for you.
So one of the things I would stress there, though, is it also depends on the kind of model that you're doing. So if you're doing a linear regression or if you're doing a neural network, you have different assumptions than if you're using a decision tree or XGBoost or LightGPM or one of those other libraries. And they mention that in the chapter, but they're not very explicit in it. So I would just keep that in mind, that the representation of your features and the model that you use are both interrelated. So you need to kind of keep that in mind. Some of them do care about the scale, and then some of them actually don't. So it just depends on the combination of those two.
One way to think about that, though, is that the random forest is just better at dealing with bad features and basically doing that transformation internally by dividing up different sections of your feature, like taking different levels of square footage. Say there's a quadratic level between square footage and price, then it would just take the lower prices and put them in one bin, take the higher prices and put them in another bin, and have them each have separate factors, essentially, that govern what your output is for that regression. Whereas the linear regression doesn't have that power, so your only option is to apply that transformation yourself.
Mm-hmm.
And a neural network similarly will do the same thing. It'll multiply, it'll divide it up and multiply them all, but it'll do a linear regression, but on different sections of the data according to that ReLU activation on different neurons.
At the very end, it talks about feature selection itself, and like just briefly touches on it and talks about embedded feature selection versus filtering and manual selection. Like from that perspective, do neural nets do more features, embedded feature selection than anything else? Or is that kind of like, do we really have a good gauge on that?
What do you mean by embedded feature selection?
It was the term at the very end.
They had
chapters 1 and 2, right?
Yeah.
So at the end of chapter 2, it talks about feature selection. It lists filtering, wrapper methods, and embedded methods.
Interesting.
It was talking embedded method selections was talking about how what decision trees do. That was their example of that. So
basically, it's via the training method you're using, it automatically does some bit of feature selection, just the way the algorithm does. It needs that entry feature where you kind of like, it picks what the entry feature is or some other piece.
Yeah, so essentially what the authors are talking about there is certain algorithms will use all of their inputs inherently, and other algorithms have the ability to essentially place less weight or effectively ignore inputs if they're just not useful. And so for those people who are, newer, I think that you don't necessarily have to get to the level where you understand intimately the math behind every single algorithm, backwards and forwards. But there are some nuances, like, for example, that a linear regression will use all of its inputs.
Unless you use Lasso or Ridge or any of the others that.
Right. A vanilla linear regression. Whereas, as they mentioned, I think, what do they mention in here? They mentioned decision trees. What do they mention? Yes, so they mentioned decision trees. By the nature of that algorithm, where it's choosing what feature to use at each split, it could just never choose a particular feature as one of the splits, and it could have zero importance in that algorithm. The other thing is they mention, and I felt like the authors did a decent job addressing the issue of scale, but not, as Ryan, as kind of you were saying, not necessarily in a way that a beginner would really understand it. And so the important issue here is there are certain algorithms where, as part of the algorithm, they will compare two, 2 points. And if comparing those 2 points involves some type of distance metric, then it absolutely matters whether or not, for example, one particular feature is represented in square feet or square acres or square miles or whatever. If you're just simply measuring the Euclidean distance between 2 points and one of your features, is that metric, then if you measure it in whatever, feet, and it's square feet and it's 1/9 of square yards, that is actually going to affect your distance metric. And typically, when you read about those individual algorithms, it will actually then reference, the importance of scaling, so that, for example, distance isn't dominated by one particular metric that's in the millions, whereas all the other metrics are between 0 and 1. But I think at a high level, if you're not familiar with those algorithms yet, that's just useful to know that, like, even if you don't know the inner workings, just knowing that k nearest neighbors measures the distance between points in your feature space. And so therefore it is very much so sensitive to the scale of your different features.
I have
a question. Sorry, go ahead.
No, you can go ahead.
All right, okay. So can I switch gear a little bit? I have a question about the differences between data space and feature space. Is that more like maybe a more fundamental concept? Can anyone explain that a little bit more, the differences there?
I don't remember, did the authors explicitly use the term data space? Because my first reaction is that those would be synonymous terms.
They did use them.
Are synonymous? I thought that what they are saying is actually there's a difference there.
Yeah, I read the same thing. In one of the graphics that they have, I think when they're doing the comparison for the songs, they talk about one's in feature space and others in data space.
Okay.
Maybe they're
Yes. So they are specifically emphasizing the raw data versus after they use the technique they just explained to you. So when they say data space, if you're doing a log transform, okay, they would say the data space is, oh, here's our raw number of reviews for this restaurant. Whereas the feature space is, after we took the log of it, here's what it looks like in the quote unquote feature space. So that's the log of the number of reviews. So you won't tend to see that in other literature that much, but because this chapter is specifically about, transforming the raw numbers into something more usable as a feature, that's the difference. Data means raw and feature space means what we've converted to that we want to plug into the model.
So how does that work, or do those differences actually between the data space and feature space hold true for the text data as well as image data? Or like how?
I mean, technically yes, but again, it's less confusing because nobody would ever make the mistake of trying to plug the raw text into, a neural network. Whereas you could easily take a raw review count, plug it in versus the log of the reviews, right? But technically speaking, yes, the data space would be the raw characters or the raw pixels. And then if you're actually in some way modifying them, technically those are your features. Features is what directly goes into the model. Again, in the context of this book, you will probably see it used much more loosely in other books.
Gotcha.
Yeah, you have to turn it into data, for numerical data first. And so you'd have to choose a representation of the natural language data, like Ted was saying, characters. You could use the ASCII number for each character if you were completely, or you could count up the frequency of characters, or you could count up the frequency of words, and you could have a bag of words, or you could have, so you have to choose your representation of anything that's not already a number. And I'm not sure whether they would consider that representation a feature or raw data or not.
I have a question, please.
Go for it, Shamson.
Hello?
Go for it.
Yeah.
Yes,
So
yes, we hear you.
yeah. So the author made mention that one of the ways to find if data is normally distributed is to use probability plot and histogram. So I was reading hands-on ML book, and I read some stuff like that before. I haven't seen probability plot have been used to check whether data is normally distributed. But from the book, I see that it's a great way to check, and it is even better than histogram approach. So in which way, or is there any particular instance where we can use a probability plot to check whether data is really normally distributed or not?
What's the context? Where do you want to know how normal your data is? And you're caring about a particular kind of feature or a particular kind of target variable? Why do you care?
Hello? No. So what my question is, first, when given the data, we need to check whether the data is normally distributed, whether it is in.
That's a normal. It's kind of it's a normal academic thing to do. People like to have some understanding of what the statistics are of their data.
Yeah.
But in general, for us engineers who are doing machine learning, we typically ignore that step and we just skip straight to modeling and feature engineering, because it doesn't really, if any knowledge about what your data looks like actually can generally lead to bad decisions in terms of what features you generate. It's not the best way to decide what to do next. There are better ways to decide what to do next. So, but you're right that if you wanted to know, if you had some academic paper you're trying to publish and you need to know whether your data is normally distributed or not, then you're absolutely right. Using a probability plot, but rather than a histogram, is a better way. But all the probability plot is doing is drawing a line, doing an interpolation, a smoothing of the histogram. So it's not really doing anything different than the histogram. It's just doing it more automatically to draw a line through it, so it's smoother and it can be parameterized. And it's it'll tell you how many modes it has. But that's more of an academic process rather than something that would be required to actually build a model.
Hi, but wouldn't that help us understand if we want to apply some kind of transformation to the
No, that's a really bad mistake that many of my students make. It's you don't transform data like squaring it or whatever to decide based on the histogram, the distribution. A histogram is just telling, or the probability. Histogram is just telling you how many large values you have and how many small values you have. It's great for determining like imbalance in a class variable or imbalance in the magnitude of your data, like, fat tails on either side, but it's not good for deciding what the shape of your residuals are on any one feature. What you're really interested in is the relationship between that feature and your target variable and whether that's nonlinear or not. If it's linear, then you've got it. If it just makes a nice line, then you don't need to do any transformations. If it makes any curve, then you've got to do some transformations. But it's all based on the actual plot, scatter plot of the actual points, not the count of the points in any particular region of space.
I think having normalized data is important if you're doing more basic statistics, like if you just want to know if you should run a t-test versus a Mann-Whitney, those kind of things, right?
Yeah, but again, that's a t-test. If you do that on any reasonable data set where you have more than 20 samples and you have fewer features than you have samples, then you will always get a t-test that says your results are statistically significant. So it's really an academic process to say how small that number is. The numbers you see out of that are typically 10 to the negative 27. It's just massively, infinitely small. It's really, really hard to create a model that is not statistically significant.
Okay, thank you.
Yeah, so from the text, I do not really understand this paragraph where he said some features such as latitude and longitude are bounded in value. Other numeric features such as counts may increase without bound. What does he mean by bounded in value?
So in this case, bounded means that there's a maximum number.
Okay.
So latitude is between -90 and +90.
All right.
Longitude -180 and +180. So you don't have to worry about unusually large numbers.
Yeah. I got you.
Affecting the model.
Gotcha.
You know, I think that I'm actually, I don't know if anybody else can share more about these probability plots. I'm not that familiar with them. I would say that figure 214 on page 29, the probability plots, it was more obvious to me looking at that probability plot and seeing how the log transform really kind of goes away from that straight line, you know, your goal line on the far right, right? It's much more obvious there how the tail on that for really large numbers isn't normally distributed, and that the Box-Cox transform, you know, is closer, right?
Yeah.
For a histogram, you know, histograms, I mean, they only have so many bins, and you know, it's a little bit chunky, and so I thought that yes, that probability plot is maybe a little bit easier to tell whether or not something is closer to normally distributed. And then what Hobson was speaking to is sort of the meta issue of, is it really important that something be normally distributed anyway, right? But if you were checking something, whether it be your residuals or whether it be your input features, if you want to check, I looked at that and I thought, oh, that actually does seem like if you want to know if it's normally distributed, like it's easier to read than just trying to squint at a histogram and say, that looks kind of like a bell to me. I don't know if other people know more statistics can comment on the probability plot.
The use.
So yeah.
There is a good use for histograms and probability plots, and that's if you are doing a linear regression and you want to know that you've absolutely got the perfect answer to your problem for your data set. If you can prove that it's normally distributed, and you can use the ordinary least squares equation, and you can have a solution that you know is optimal, and you don't have to do anything else except transform your data to make it that normally distributed. But once it's yeah, but that's only if you're limiting yourself to a very simple model and a closed form solution where the assumptions of the model assume that you have to have, in order to guarantee optimality, you have to assume that it's normally distributed.
There's some, I'm not trying to sell R to anyone, but there's some really good libraries for stuff like that because it's so statistically motivated, right? And there are some non-parametric options if your data doesn't meet the assumptions of the kind, like the sort of interpretable model you're trying to go for. It seems, I don't know, my data is literally never normal. I don't know why I learned so much about freaking parametric tests when I never have to use them. Anyway, that's what I'm mad about this week.
Yeah.
We missed most of your anger, so that's probably a good thing. The audio cut out.
As well. It's irrelevant to stats, I guess.
Yeah. So I might understood it wrong. What I understood after reading the text is it seems like some algorithms assume the data to be Gaussian. So in that case, you need to normalize the data, right? So
if you want to ensure the optimality that those assumptions are based on, those assumptions just tell you an answer. They say this is the optimal model. But if you don't care that you have the optimal model and you just care about your prediction accuracy or something else, then if you don't want to know that you're done with your problem solving, then you don't even have to make it Gaussian ever.
Another way that I might reference that is that, you know, I think that that machine learning really started with statistical modeling and was once dominated by parametric models. I don't know if everybody has read this or referenced this, but there's that Leo Breiman paper, the two worlds, the two models, whatever, but basically where he talks about statistical models versus algorithmic models. And of course, he's Mr. Random Forest, so of course he was arguing that algorithmic models, even if they have no statistical basis and you can't calculate a standard error, that they have a place. And that Leo Breiman paper was from 2001, I think, 20 years ago. So I would argue that machine learning has very much so moved towards the algorithmic models. Everything deep learning, falls in that category. Gradient boosting machines, random forests. So basically, like, all my favorite models are algorithmic models, not parametric models. And most of those no longer have nearly as many requirements around the scale, the range, the shape, the normality of your data.
It's going to be another 20 years before professors stop teaching that approach, at least. And it may continue to be cheap because it's a really difficult skill to learn. It's kind of like your gatekeeping on math. And then once you learn it, then you have at your power, you can design better algorithms, knowing when you can prove that something is optimal, or you can prove that what the assumptions are about the distribution of your data. All of that becomes really valuable if you're actually trying to design new algorithms. But beyond that, it's not so great for people who aren't grad students trying to do something new.
So it was a great question. I hope this discussion was useful.
I'll try to find that paper. How do you spell Breiman? In the chat.
B-R-E-I-M-A-N, I believe.
Thank you. I got that really wrong. No wonder I couldn't find it.
There was one other thing you mentioned about not being able to calculate standard error. And I think you can still assume Gaussian distribution on your error, especially if you see a plot on your probability plot on your error that looks Gaussian, because it often is. In fact, most of my models it is. Because your model is going to heavily weight those in the meat of your curve. So you're going to tend to have zero bias in your model over all your samples. You're going to end up with a mean of 0, and you can typically, and it's usually balanced on either side, your error. It's pretty rare to have, unless you've got a lot of outliers on one side. So you can still calculate a standard error. You can still calculate a z-score. You can still calculate confidence intervals using the standard, 60, 68, 95, 99.7 rule, without having to know any statistics at all. Just do the STD on your errors, and that's your root mean square error.
I have a couple different things that I want to show. So I'm going to share my screen briefly, and then we can talk about a few things. So one of the things is we've been talking about if you want your features to be Gaussian, if you want them normally distributed. And there's two different things there. So sometimes you want to manage the distribution of your feature, but sometimes you also just want them to be on the same scale. So like in the linear regression model, if you have something where it's like number of bedrooms and it's typically just like 0 through 5, basically, and then you have square feet, and that might be 0 to 5,000, for example. Your linear regression is going to have to search through this space that's elongated like this. And so as it's making its updates, it's going to potentially have to wander further, or it's going to have issues with convergence if the values are on a massively different scale. So there's value in scaling and normalizing, even if it's not to fix the distribution, but rather just to get them on similar scales of between 0 and 1, or whatever is appropriate for your model. So if you can take something like this and just rescale it so it looks like something like this, then it will converge faster, and you'll have better properties of your model. I just wanted to showed that, because I think that's important to understand too.
Yeah, totally. Scaling, linear scaling you can never go wrong. It never reduces your model's ability to fit the data fast and correctly.
And Ryan, on that point, would you say that in time series type of model, the feature scaling will be more necessary? Like if you're looking at decades of data, I'm sure like even the stock market will be in a different scale. Would that be, or comparing like even the same kind of data between different markets, different countries?
Yeah, the typical way that that's handled is by either taking the log of the data or just looking at a percentage gain and a percentage loss every day. And it's usually the delta that people will often take the time difference between two dates rather than the absolute value. That's another way to keep it close to zero and keep it small and keep it all on the same sort of scale.
Right, but is that typically a common practice in this case? Like, because I feel like the book actually spends a lot of time or a lot of chapters on image data or text data, but I mean, this current chapter is about numeric data, but I'm wondering whether or not there's a common practice of always applying some sort of feature scaling on time series data or variables that we know that they are on different scales.
You can take your time series data and essentially turn it into an image or turn it into a table simply by moving the time series and making it a row, and or making some portion of it a row. A rolling window is typically what's done. So you end up with like today's price, yesterday's price, the day before yesterday's price, and the day before that's price. And so you have 4 new features, and those are all scaled using all the techniques described in the book, including the one that Ryan was talking about, where you just linearly scale it to all be between 0 and 1 or something.
I would add, I don't think that you really want to, I wouldn't focus on applying what we just learned to time series yet. I don't think that it's really applicable to scale in that way. But what I can add is it's pretty common on the time series stuff to do what Hobson said, which is, so I built one in driverless that's differentiating. So you basically just take the difference between 2 different time points. And that's a really good way to normalize time series signal, because it might be the case that you have values that like a stock price for, if you're looking at Tesla or something like that, your model basically breaks if it starts going above 1,000 and it's never seen that value before. But if you just look at the difference between days and you say, okay, it gained 10% value or it gained 2% value, it can still learn from its history of it's seen a 10% gain before, it's seen a 2% gain before. And so that's a way of making it so your features are correctly scaled, even if it's not in absolute units, it's just in percents or something like that. So that's one way to deal with time series scaling in that sense.
Thank you.
So one of the other things I wanted to bring up, this is all inside of driverless. I'm not trying to do an ad for this. It's just something that I was working on in the past couple of weeks, so I think it's kind of relevant. So I built a simple linear model inside of driverless, and it's running on the same data set, the same everything basically. And this is the performance of a sklearn SGD regressor, or classifier rather. And this is the performance that it gets. It gets this AUC, higher number is better. And so this is the unscaled version, and these are the variables that it found important. And then this is the performance after scaling. And so it's able to get to a much better score, because previously some of these variables actually have really high values, like in the thousands or something like that. But the variable that is actually important is this ext source, and you can see that its values are all very, very small. It's like under 1. So just basically just adding in the min-max scalar from sklearn that just scales all of the features to be between 0 and 1 gives it this large performance boost just by putting it on a consistent scale, which makes it easier to find the features that are significant and actually useful.
And I want to reiterate, yeah, the scaling from 0 to 1 would also work in your case, Becky, if time was a column, one of your features, in addition to the price or whatever it was. Even when the price grew above a price you've never seen before, because you would have at least one linear feature tracking time, they would be able to, there would be some scale factor on time that would handle the growing price over time, the overall general trend in time. And so that will be taken out of your model, and your model will be able to deal with prices above what you'd ever seen before. So it is possible to shoehorn it into the kinds of things that they're doing here and that Ryan's talking about with the scaling. But like he says, it's probably faster and better to actually do what people would find works really well on time series.
Gotcha.
One of the other things I wanted to show is within sklearn, they have this nice series of graphics and explanations of the various different scaling options. So if you're ever curious about applying different techniques there, they have these nice plots showing basically the distribution of the original data, and then the various different scaling attempts. So you can use the standard scalar, the min-max scalar, which is the one I ended up using, max absolute scalar, robust scalar, and these are all doing various different things that are kind of in line with what they described in the chapter. So they showed them doing them basically by hand, but with these, it just does it automatically for you. So I wanted to kind of give these a shout out because you don't need to do it manually like they did in the chapter.
Exactly. And it takes care of the bookkeeping, which makes it really important when you want to know what your features values actually were on your inputs before they were scaled. So if you want to understand, at what point a particular feature's value is causing your prediction to change.
And then one of the other things they pointed out was binning, or splitting based off of the quantiles. And I wanted to point out that there's also a option within sklearn to do the similar thing. So in their examples, they use pandas and its qcut function in order to split it into, okay, here's the bottom 10% of data, the bottom 20% of data, 30% of data, and so on. And they made a bunch of bins out of the data. And they just split them into 10 different pieces. And I wanted to show that you can do something similar in sklearn, and you don't have to kind of do some more manual coding. This will just automatically do it for you, and it will also remember your cut point. So if you have some training data and you want to apply it to your test set, for example, it will remember your bins, which is not going to happen on your on the pandas example that they showed for you, and that's actually kind of important. This also has some nice things in that you can just define how many bins you want, and then on top of that, it has various different strategies for determining the bins. So you can split it uniformly based off of the quantiles, which is what they did in the book, or you can do k-means, which will basically try to find various different groupings of the distributions.
Oh, very cool. So you can turn a continuous variable into a class variable.
Mm-hmm. Yeah.
So is there a way to define the number of bins, or is it a hit and trial method?
Is there a way to find like the optimal number of bins? Is that what you're asking for?
Yeah, like what's the strategy that we use to find that number of bins? So we start by 5, we start by 10, or how does one approach to find the number of bins?
I don't know that there's really an optimal.
There are actually a couple optimal. So I've looked into it with k-means. I'm pretty sure it's the same for k-bins, but if you know the fundamentals of what the k-means algorithm is really doing, so it's like splitting the data at a random 2 points, so like 2 clusters, and then calculating the distance from every point, taking the square residual, and keep testing that for more and more bins. There are a couple of things such as the elbow method and silhouette method where it's looking at the difference. So what happens is as the more bins you do or the more clusters, the overall distance starts to rapidly decrease. And there are just various ways you can analyze optimal bins. And there are libraries that do it for you. But the elbow method and silhouette method, they're pretty standard. They'll give you plots of residuals of, I think it's measuring the distance between the cluster to the closest point and showing how it decreases. And you could just try the 3 closest to its recommendation. But if you want to get more into it, there are other ways you can find optimal bins. But that's just a pretty straightforward way to get an answer to that.
Yeah, that's the way that tells you whether they're optimal from whatever that metric is you choose. There are a lot of, there's a whole page with, I think, like 20 or more possible metrics for evaluating clustering.
I think the library is the yellow brick, where they'll basically do that for whatever metric you want. It'll just calculate it on its own and give you the plot. But the simple one is just Euclidean distance, but you can input whatever measuring metric you want to do. They have 20 plus and they all have their pros and cons, but what I found is typically it's all going to center around the same amount of clusters. But yeah, they have different analysis for that.
I would warn, however, that so there's a whole, so it's sklearn metrics and clustering. That's the package that has all these other metrics. And the reason why there are so many different metrics is because there are different things that are important for different problems, and like, for instance, deciding at what threshold the silhouette score is good and when it's bad, or deciding at what threshold where the elbow in an exponential looking curve is, deciding where that curve is curvy is really hard. And so most people, at least what I do, I don't ever look at any of those plots or metrics, and instead I just look at the thing that I actually care about. And it's usually the root mean square error or the actual the end product, whatever the error or performance or loss that I'm actually doing on my test set. That's what it's just like any other hyperparameter. You try going up and increasing from 5 to 6. You start with the default, then you go to to one greater and then one less, and you see if your error got better or worse. If you can afford the time, and as long as you're not working with a data set that takes forever to train on, you can do that.
And just to clarify, what those libraries that are doing, like the library that'll try to give you the optimal plot, it'll actually do like a k-means for, and then you can suggest how many you want. Like I want it to do it for 2 to 30, and then it'll give you all those answers in between. So you can pick out that way also, but it won't measure your end goal, whatever statistic you're looking at. It'll just measure the distance between clusters to the closest point or whatever you want, whatever distance you want to measure, but it'll do it for every amount of bins you really suggest.
Oh, absolutely. It's just that, I find that that's also often misleading. It actually sends me in a direction that's not working for my particular problem.
So the way that I've configured it to work within driverless is we basically have the option to do any of these. So the way that I look at it in terms of the k-bins discretizer is you're just determining how many decision points to give your model and how much information to throw away. Those are the 2 things that you're trading off. Because in theory, you could do 1 million bins and you have a continuous variable and you've just cut it into a whole bunch of tiny little pieces. And you've given your model a whole bunch of expressive power because it can differentiate between every single continuous feature. But that's probably not useful. You probably want to limit the bins in some way. But the trade-off there is then you're losing precision. So if you only have 2 bins, then you basically have a binary variable. You're saying, was it above 0.5 or below 0.5 or something like that. So as you're adding more bins, you're giving it more precision. But depending on the size of your data, that might not be useful. And specifically in this case, I was building something that was intentionally designed to just be simple so people could look at the results and interpret it. But inside of driverless, it's trying these various different options and seeing the relationship that has on model performance. So it's directly looking at the RMSE like Hobbs was mentioning, and it's trying the different strategies and saying, is there some way that we can cut this that will be most useful for the model in order to make accurate predictions?
That's another really good point. You can't just look at just the tested accuracy in order to find out whether it's too many bins, because your training set accuracy will always get better as you increase the number of information capacity. But if you're overfitting, then when you get a big separation between training and test, so you have to look at both.
Mm-hmm.
It's useful to keep in mind that if you've got measurement error, then a certain amount of binning can actually help you, because you're moving all the measurements to what would be the average of a particular.
No. The binning never, ever, ever improves the accuracy of your measurements.
No, when the measurements are in error, that you're binning.
They're always, all your measurements are always in error.
Nevertheless,
you can
demonstrate better performance when you do some binning on test data.
Yeah, that's a common misconception, but it just doesn't help.
It's not a misconception. It's absolutely true. And in fact, if you go to, like, for example, XGBoost or any of the other gradient boosting, there is a built-in binning going on from the beginning.
That's just because it's required for the algorithm, but
it's not required for the algorithm. You can split on every possible value in the data. No, it's absolutely the case. And you can see that in some of the learning machines. An old one, KXEN, for example, got its better results because it did some binning.
I'll have to look into it in order to understand that. But
I'm dead certain about this. I didn't start this yesterday. I've been in the field for 30 years. You know, and I'm glad someone mentioned Leo Bryman. I used to work with him.
Okay, I have also been in this business for 30 years. So
okay, no. So I mean, so it's not a matter. I don't want you to dismiss me because you think you've never heard me say anything before, and I might be a beginner. I'm not a beginner, and I'm telling you that binning can actually help.
Great, you give me a new idea to look into.
Measurement error. Anyway, so and you were so certain that I was wrong, so I'm just making a point that I'm not wrong on this.
Wonderful. I'm still quite certain, but.
Okay, well, we can take it offline sometime. We can continue. I'll look for some examples in which you can see how it works. Anyway.
Yeah, exactly. If we can, I'll do an experiment, and you can see if I'm making a mistake.
So Ryan, I have one more question. So you mentioned about binning and also scaling. Do you recommend or how is it normally done? The scaling before binning, or after the features are being selected into their bins, we do the scaling for each respective bins?
So the scaling and binning, the order, once you bin something, it doesn't, the scaling is irrelevant, because the scaling is just putting it on a different, so let's say that you have square footage or something like that, and it's 0 to 5,000. And then you rescale it to be between 0 and 1. If you do binning after that, it's just going to be choosing different cut points, but it's not going to change the actual representation of the data. It might just choose 0, 0.1, 0.2, 0.3 instead of 0, 500, 1,000, 1,500, for example. So once you do binning, the scale no longer matters. And at that point, it's going to be binary variables. So it's going to say basically, like if you're familiar with one-hot encoding, it would just be like 0, 1, 0, 0, 0 in order to represent 1,000, for example, if that's the second bin. So that,
I think the key thing is that all the points would still stay in the same separate bins.
Mm-hmm.
They're not going to change. Like a point's not going to go to a different bin regardless of whether it's scaled or not.
Yeah.
Right, but what if? But I guess I have a related question about that too. Like, what if you have, let's say, two totally different variables that are both are binning, and so one you choose 5 bins and the other one is 20 bins, and in a way, it feels like you are applying 2 different scales. But I totally get your point about it's like binary, like you are now like just a yes or no thing. But my confusion is stemming from that, like, if one is house price housing pricing, and the other one is age, for example. You may apply different levels of bins, but then they are still in different scales, so to speak.
So if I could try to jump in, I think the simple answer is that when you do binning, that is a form of scaling inherently. And Ryan was giving some of the technical details. So for example, if you had that square footage and it was between 0 and 5,000 and you do 5 bins, okay? It's not like you have a bin that's called 5,000 and a bin that's called 4,000, right? At that point, you know, you just have bins that are just, you know, either one hot and coated, or they could be just bins 1, 2, 3, 4, and 5, right? But so, and that was a bad example. I said 5,000, 4,000. So let's say you had one bin that's you know 1,000 to 1,200, another, you know, it's a small bin, another one that's 1,200 to 1,500, and your top bin is 2,000 to 5,000, right? So it's by taking all of that and compressing it into one bin, just called bin number 5, right? You've actually, you know, scaled it. So sorry, I didn't mean to say as much, but so to the earlier question, binning is in and of itself a form of scaling. So you would never apply scaling after binning, and scaling before binning wouldn't really change the binning either, for the most part. So so I don't know, I hope that helps.
So one of the things that I want to show here is this, I'm still showing my screen, right?
Yeah.
So what this feature importance is showing is I've split this ext source 3 feature into its bin. So it was originally a continuous feature like they were showing in the book. It's already between 0 and 1. And then when you do the binning process, it's actually one hot encoding it, so it's splitting it into its different bins. And each of these is just set to 1. So if the variable falls in this range for a single row, then it's going to be a 1 when the feature is between 0.0 and 0.13. And this is going to be a 1 when it's 0.13 and 0.18. So there's no scale to these features. It's just 0 or 1. Is it between this range or not? So they're
right. So true false represented as 1 0.
Mm-hmm. Yeah, exactly what he was just mentioning. I just wanted to show the actual example of it.
So Ryan, this particular example, and you showed the improved metric, what type of model, what base algorithm?
So this is, just out of sklearn. This is just a SGD classifier. So it's just a linear regression, but it's found with gradient descent.
Yeah, no, I was just checking to make sure that fundamentally it's a linear model.
Yeah.
Because like if you were using a tree model, I wouldn't expect you to get that value from binning, since the tree can sort of inherently do its own binning by picking cut points.
Yeah. So the last thing I wanted to show before I quit sharing my screen is that in the book, they mention the scaling of the features, but you can also do scaling and transforms on top of the target. So that's something that's actually very useful if you're doing something like, I'll just stick with that house prices example. Most houses probably fall within some certain range, but then there's Elon Musk's house and it's $100 million or something like that. If your model isn't properly tuned to do that, then it's never going to be able to make a prediction of that magnitude. And you can get there by doing various different transforms. So if you take the log of it, then it might make it so your model's just predicting the most it ever predicts is a 9 or something like that. And so just getting that extra step to a 9.5 is significantly less than getting all the way from 100,000 to 100 million. And so in driverless, we have these various different transforms, and they're almost always useful. They almost always get used that applying some transform to the target is useful in getting better model accuracy out of it. I think that in the book, they showed these various things, but they didn't really show their relationship to how it creates a better model. Even in some of their examples, they were showing, oh, you can do the log transform and actually it does worse. I think that they should have found something where it actually made an impact on the model, because without showing that, I don't think it
That's right.
would look very useful.
So Ryan, I had a question, and I apologize, but in addition to reading the chapter, I was also skimming ahead in the book a little bit to just try and be prepared for next week. And I also read a number of articles that were on this topic. And so I can't remember if this was mentioned in the book or not. But, you know, some of these things are less important for tree-based models. And so if you're a big fan of XGBoost, there's, you know, there's less importance there. But one of the things I was wondering about is, and I can't remember for sure, I thought it was mentioned in this chapter, but dealing with potential outliers, and I ran across multiple references to Windsorizing, and I was curious whether or not in problems that you've worked on or in driverless, to what extent you've looked at the potential utility of trying to tame some of those extreme values.
I've seen that in various books, but I've never seen it on Kaggle. I've never had my own experience with that really being useful. So I'm sure there's some scenario where it is, but I personally have not encountered any scenario where that's been a benefit to the model, really.
Can I ask you, Hobbs, like if you're building a neural network, wouldn't it potentially have problems with some extreme values?
No, I don't think so.
So like, let me give you an example. So if I had data, raw data that had some extreme values, and I just do my natural thing where I scale everything between 0 and 1, because of those extreme values, all my actual values might get scrunched between 0 and 0.001 instead of kind of more spread between 0 and 1. And couldn't that be a problem either for convergence or for accuracy?
I think the very first layer will have, you know, all the weights of that first layer multiplied by that to compensate for that smallness. And it will just have larger weights on that layer.
But then wouldn't those outliers then get ginormous values?
Well, a neural network would have a lot more flexibility to deal with it, because then it would have a ReLU where it could chop it off at whatever point it wants to at the very next layer. Or it has some non-linear function that's going to transform that to be within. That's the whole. I think that's what the first layer's main purpose is sort of scaling everything and getting it non-linearly transformed in a good form for the next layer.
So that's where the stuff where like taking the log of a feature and something like that is useful, because it scales it in a non-linear way. So if you just apply the min-max scaling to it, it does completely crush that entire segment to be like between 0.01 or something like that. But I don't know. I've typically had better luck with preserving the data, because in essence, what you mentioned, the Windsorizing, I haven't used it a ton, so I don't know the full details of it. But just clipping and various other techniques like that, you're throwing away detail, and it's probably better to just do some sort of scaling to keep the actual like information there, but put it on a different scale.
And also, if you're using a decision tree-based method, then the outliers in the predictor space are irrelevant. Doesn't make any difference. Because the tree can't even see the actual values. All it sees is the ordering of the data. So can't tell the difference between 1, 2, 3, 4 or 1, 2, 3, 400. Those two are the same order. And to the tree, it's the same. So you don't have to actually do any kind of scaling for a tree-based method, which is why they're so attractive.
Yeah, thanks, Dan. That's a good point. I was really thinking about, you know, these deep neural networks and sort of the concept that, like, if the only thing I had was a function that was y equals x squared, and even though, right, a neural network is doing linear operations, it could very well train and do a pretty good job approximating, you know, x squared, if that's your target, right? But the issue is, if you had a lot of features and it needed to square all of them and whatnot, then depending on the size of your network and the complexity, would it actually find? Yes, you know, it is possible that it would find the perfect, you know, set of weights to exactly mimic that output function, that feature space. But would it actually find it when you in practice, right? And so that's where I was kind of wondering about how, for example, like a log transform may not affect whether or not there's a theoretical set of weights that does what you want, but actually your likelihood when you know, do your gradient descent that you actually get a very good local optimum.
Yeah, representation does matter a lot. It does affect the training time, and it does affect the likelihood of you getting to that minimum. And there are some like even that square term, it's going to approximate it with the layers. And if you don't have enough layers, the approximation is not going to be good enough. Only the tree method that Dan was mentioning would actually deal with that perfectly. But I think there's a little bit of treeness in most neural nets in the sense that there's usually a threshold. There's usually ReLU layers along the way. And so it can kind of bend it into whatever bends it needs and apply a linear scale at that point. And then, so as long as you have enough neurons for it to do that, I think you can usually approximate a tree method with a neural network. It just takes a lot. It's actually more general than a tree method. It just takes a lot longer to reach that optimal set of weights.
Thank you.
So I guess, so to summarize, the recommendation is to, if you can, do a transform but not scale for deep neural networks. Generally.
The recommendation is, if you know of a transform that's going to make your data easier to learn, then do it. A scale that's going to make your network better, then do it. If you don't know, then try it and find out if it improves it. There's because these things are, I often forget what's going to work and what's not going to work, and I often have to retry them but some of the things I've been saying are just based on what I remember having seen in the past.
So is it fair to say that, like, for a gradient boosting machine, a log transform is unlikely to make much of a difference if you just log transform one feature?
Won't make any difference at all. Right. To the tree, log x and x are the same.
Right. So that's where, Tommy, for a deep neural network, yes, it is something you would consider because it could make a difference. Even though theoretically maybe it's possible for it to optimize either way, it may not in practice. And so therefore you would, it's a reasonable thing to try these transforms on your inputs.
Yeah, I don't want to quibble about details, but I think that even in a tree-based method, a log transform can sometimes help because a tree-based method has a limited number of trees in the same way that a neural network has a limited information capacity as well. If you can get the data into a form that is more meaningful and more closely represents your target variable and the things that matter to your target variable, if it actually measures the physics of the problem, you will always produce a model that trains faster or gets to a better error, a lower error, no matter what the model type, because you're simply creating a mathematical formula to predict, and that mathematical formula has a certain number of degrees of freedom. And sometimes if you can make that, if you use up more of those degrees of freedom, doing the transformers internally, the feature engineering internal to your, as I call it, the embedded feature engineering, then you're leaving less over to actually model the physics of the world. I'm thinking of, like, if you think of the simple problem of orbital mechanics, if you represent orbital mechanics as XY positions and you try to plot and model what what the gravity vectors are and all about going to the moon and coming back, and what thrusting you need to do to get to the moon and come back, you'll be sorely lost in space, and unless you put it in a polar coordinates around the dominant gravitational body in your system. So so representation does matter a lot, no matter what your model. It's just, you can get away with it a lot. You have a lot more information capacity and a lot more flexibility in tree-based models and neural networks.
Yeah, so Dan, would you agree that in not a classification tree, but a regression tree, that that sort of manipulating your input features may make life a little bit easier for even a tree-based model? Like, square root versus square, that type of thing?
Here's the thing, the tree can't see the actual values of the x's. It just knows the ordering. And so if you make any kind of order preserving transform, so if the order of the data is the same after and before the transform, or reversed,
it also sees the number. It sees the number of points within a range of values. But I guess if the order is preserved, then that number of points will be the same no matter where you draw the lines.
Exactly.
Right.
Exactly.
Yeah, the point I'm trying to make is slightly different. So in a regression tree, then there are different strategies for potentially like interpolating the leaves and things like that. And so that's where I'm wondering whether or not, again, something that more accurately represents your problem, like square footage for a housing price prediction problem instead of linear measure. Again, it won't change the splits available to the tree at all because it's order preserving, but it might actually help the accuracy of the final, numeric regression prediction.
Well, your prediction from a tree, and this will be the, it's modified, of course, if you have lots of trees, but if you have one tree, then the prediction is the average value of the target in that terminal node. So once you've got the set of splits that get you to that terminal node, then it doesn't make any difference. You get to the same terminal node, you get to the same prediction. Now, the trees will differ if you change the scaling of the y, the target. So if you use log y instead of y, then you're going to get a different tree. And that may be a useful thing to do. But if we're talking about the features are the x's, and there it's not going to make a difference.
But aren't there modifications of the basic tree algorithm that don't simply use the leaf value, but actually look at distributions within the members of the leaves?
You could, for example, besides the mean, there's the mean, there's the median. And then, of course, if you're talking about gradient boosting machines, then the output of the trees has got nothing to do with the mean of y there. It's actually based on the log likelihood that you're trying to maximize.
Yeah, no, what I'm specifically referring to is if you have a leaf that has, let's say, 10 values between 2 and 3, that when you're making a prediction, if you wind up in that leaf, it will make a different prediction whether your actual input was at 2 or at 2.5 or at 3.
Yeah, there have been various experiments with, suppose that you split the data where anything that's 2 or less goes to the left and above goes to the right, but your training data has 3 and above. Then, the standard approach in decision trees is to make the split point at 2.5. But it doesn't, if your data only has 2s or 3s, then it doesn't matter where you make your split point. It could be 2.1, 2.9, it's the same. But if you're starting to get new data where the values could fall in between 2 and 3, then it's going to make a difference as to where you choose your split point. And in fact, there's a variation of random forests where you actually make that split point the value going to the left and the value going to the right, and you pick that at random because you don't know what's coming at you in the future. And that actually can improve performance. But the norm is that you just pick the midpoint between the highest value going to the left and the smallest value going to the right.
Thinking about it as a sorted.
I'll take this offline. I don't want to beat a dead horse about making predictions from terminal nodes.
Oh, okay.
So I think the last thing that we haven't touched on out of the chapter is interaction features. So they showed some techniques about actually saying, they're specifically looking at the linear models probably and saying, okay, what is the relationship of these two things is probably important. So let's say in the house price example again, let's say someone has a house and they want to maximize its resale value and they see, oh, everyone's model says you just need a lot of bedrooms. So they made 100 bedrooms and each one is 2 square feet or something like that. And so they played the model and they have figured out that they can manipulate it in such a way. So a smart model would then look at the relationship between square footage and number of bedrooms, and they could infer, oh, it doesn't make sense, all of these bedrooms are way too small. So what they're showing in the interaction features section is you can do the pairwise interaction. So you could say, let's multiply all of these two values together, all of the different combinations, or divide them, or do some other relationship between them. And you can get a deeper representation of the data because you're not just looking at each variable individually, you're looking at the relationships across them.
You can see how powerful that is on the playground, TensorFlow playground. They have an example where if you just have data that's in 4 quadrants, diagonal from each other, it takes twice as many or more neurons to fit the same data if you don't have that multiplication feature. And so if you double the number of neurons for each and every feature, you've got to, or if they have any kind of interaction, that's for that interaction. And that's the concept that Dan was talking about, those transformations that preserve order for an individual feature, those are the ones that were most, the tree-based messages are going to take care of automatically. I mean, I think he's convinced me that that's it's not going to affect anything because it can't really see it. It can't change the thresholds, but it's those non-order preserving transformations and those interaction transformations that you can do. Those have a big effect. Like I'm thinking of like the sign transformation for a single feature, and then Orion's multiplication of 2 features, or and so still thinking back to my orbital mechanics example, because
I just wanted to say something about interactions, because last year I was doing some experimentation with a colleague of mine where we were working with artificial data. We were trying to work with data that might be a bit similar to what you find in bioinformatics. So we worked with about 100 variables, most of which were noise. And we created a few interactions among a handful of variables that were actually important. And we were unable to detect those interactions using a lot of different methods. I thought we were going to nail them with some of the tools that we have used to modify gradient boosting machines. And I was just stunned. Now, the interactions weren't that strong. Obviously, if you make them super strong, any method will find them. But I was stunned by how difficult it was to find a moderately important, but not overwhelmingly important interaction. I don't know what to make of that. We have not finished that work, but I was shocked by the results.
How did you find it? Just by random search of the pairwise multiplication?
So we were actually using the gradient boosting machine because it finds interactions on its own as it builds the trees, but we couldn't find the right interactions.
But you did eventually find them. You said you did find what?
Well, no, we created the data, so we knew what the truth was, and then we would look at models we were showing versus the truth, and it was like, what is this? How come we can't find it?
Oh, got it. So that's the real problem that happens in genomics. If you figure out a technique that can find those interactions, when you have 1 million features instead of 100 or 1,000, then you've really discovered something that's going to change the world.
Then I'll be living next to Elon Musk.
I do have a question about the interaction, the interactive features in practice. Like Ryan, in your models, how often you kind of evaluate that, or how, like, yeah, maybe Ryan, you can comment first.
So like they were mentioning, in gradient boosting machines and in neural networks, it will try to find those interactions on its own. So I typically have not needed to do any sort of manual engineering or just doing all of the pairwise interactions in order to get the signal out of the data. But if you are doing a linear regression or something simple like that, then you probably do in order to get that relationship out. One of the things that we do inside of driverless is there's various different kind of aggregations and groupings that you can do. I don't know the full inner workings of that, so I can't really speak to it, but there are ways that you can look at the relationship between variables without doing the full like pairwise. One of the things that they mention in the book is that that can massively blow up your feature space.
Right.
Because if you have 100 features, then you have whatever 100 squared is, and you just have way too many features for your model to even be able to suss anything out of it. But
like what you showed earlier in the list of kind of important features that you have identified, wouldn't it be nice once you have identified what features are important and then you kind of go in and really create that kind of interactive features on top of those and see if those things make sense? Or
it might actually, you might actually get a lot more power if you find that some of those zero influence variables actually, when you combine them with something else, becomes extremely significant, because often the significance is hidden in those ones that are not yet important.
Right.
And you're already getting a lot of information out of the ones that are shown as important in your model. And so it's those others that you really got to work on.
Right, but since it's so expensive to look at all these, I mean, possible significant interactive features, I just don't know how that is being done in practice.
Yeah, I don't know what AutoML does. I don't know whether it starts at the top or the bottom or does some random search. But
so there's
in most cases, you can kind of get a feel for which ones should be together. Mostly, sometimes domain knowledge can help you. If you know that these variables are associated with one particular city or one or kind of person, or if they're associated in space, like in an image, then we apply filters on those combinations like CNNs and such. We come up with algorithms that deal with things that we know about the world and the problem.
There are some stepwise forward regression techniques. You can imagine, suppose you had 100 variables, and you know that all the interactions, that'll take you to 10,000 divided by 2. Right. But you don't have to create all those interactions beforehand. You can do it on the fly. So what these methods will do, and I think the first one was published around 2000 by a couple of economists that were looking at some automatic regression methods. And they were trying to say that they could beat machine learning in this famous paper, but I can't remember what it is. But what they would do is they just keep the 100 in memory, and then they dynamically create a new temporary variable, which is an interaction, and then they test it for good enough to enter the model or not. And they said that their technique was very fast. And also Jerry Friedman's Mars, Jerry Friedman, the guy that invented the gradient boosting machine, he wrote Mars in 1991, was a stepwise spline generating regression methodology, but it also does stepwise interactions if you allow it. And it's the same kind of thing. It won't allow an interaction to be tested until at least one of the two variables is already in the model. So there's a way of keeping down the search space. And I'm not sure, I never liked those things, but people were asking, well, how do you do it in practice? And that's the way it's done. And I'm sure, like the one I mentioned, that economics paper from around 2000, it was published in JASA, Journal of the American Stat Association. There is an R package, that implements their method. And they said they figured out ways to make it go very fast. I'll find it and I can then post it to the group later.
I think it's called Earth.
Oh no, Earth is actually not a very good Mars, but it is a Mars. But this thing is actually stepwise regression, not a spline regression.
Oh, cool. I'd be interested in seeing what that is.
Yeah, I'll look that up. I haven't thought about that paper in years, but it made a splash, and they came up with some good, really clever computational tricks to make it go fast.
Yeah, that's a general principle in all this feature engineering, is if you just look at one feature at a time, you can even just add it to your existing model and see if there's any kind of statistically significant boost in your accuracy. Testing one additional feature is not usually very computationally efficient, especially if you're using something like linear regression that's closed form. You know exactly how long it's going to take. And then your n squared combinations is you can know exactly when you're going to be done, and you know exactly whether you can be optimal in terms of knowing how many of those, I mean, how likely it is you've missed anything. Like you can be certain that you haven't missed anything, any pairwise combinations.
Did you want to show something, Ryan?
I was muted for a second, hang on. So I pulled up driverless again just because I wanted to show how things are kind of organized within driverless, and we have this ability to limit the interaction depth. So you might want to look at just they called them singleton features in the book, or the pairwise interactions, or the third order interactions. And by default, it's able to do as deep of interactions as you want. So you could do the relationship between 4 variables, 5 variables, etc. But it does that with a underlying algorithm that's trying to look at the relationship with performance, and very often that doesn't yield any additional benefit, even when it's doing an automatic search across tens of thousands of features. So what I've found is that it seems to, rather than actually find significant interactions, it just kind of exploits features that it likes. So if it has one feature that it really, really likes, and it's using gradient boosted decision trees, part of that mechanism is it will take a portion of the data and a portion of the features. And so if it just generates a bunch of kind of variations on the one feature it likes, then those features will happen more frequently in the trees. And so it kind of cheeses its way to get the feature more by faking feature interactions. So
Yeah,
go ahead.
You'd probably have to have a problem where you know that there's some interactions variables that are actually helpful. And to Dan's point, do you have, or a question to you is, have you ever seen at any point where a pairwise combination didn't show up in a triplet combination? So that if you got a slight boost in your pairwise, you could know then to only try triplets on that pairwise. Does that make sense?
It makes sense, and I know that that's how Mars works, because you can't get to a triplet unless you've got a pair that's a base, and then it'll try to add different variables to that pair to see if they make any difference. But were you saying that you were wondering if you could ever have a triplet, but you don't need the pair?
Exactly.
Well, you know, because the way Mars works, you know, and we don't want to get too much into this, you know, relatively obscure technology, but it does forward stepping and then backward deletion. So the pair has to get in, then the triple gets in, but then in the backward deletion, the pair might be deleted. So it's possible, but I've never seen it happen.
You can do without it. It's just you have to get there by you can get there faster by not trying all the triplets and instead trying all the pairs.
Yeah, I think it was an efficiency reason that Friedman decided to do it that way, especially since he did it in 1991 when computing power, Amazon wasn't around then.
Yeah, n squared is much better than n cubed. Exponentially better.
Yeah, so here's, I don't know if that's a good example of it. I'm trying to see if I have, because in driverless, it shows when it finds some interaction and it'll say, okay, here's the relationship between this and this and this. And it groups it in various different ways. I don't know if I have any good examples of it. These are all target encoding things that are a little bit different.
Were we seeing any triples there, or multiples other than 2?
In a sense, yeah.
Yeah, that does seem like it's just kind of cheating to try to overemphasize some points, because if you're not seeing pairs that are significant, but well, I don't know, maybe it did do, like Dan was saying, it got rid of some pairs.
So sometimes it does wacky stuff like this, where it's saying it's looking at these 5 different variables. It does the truncated SVD on top of it, and then it pulls out the top 2 components. And what I've found is it kind of is just finding its favorite feature and then just
using it multiple times.
Yeah, just duplicating it. Sometimes it's hard to sort through. This only happens if you set our
that make blind feature is there a couple times.
Mm-hmm. Yeah. One of the other things is we have a trade-off parameter where you can so we have these various transformers in here, and it's kind of like what Becky was saying, where you might only want to exploit things that have already looked useful, or you might want to explore more. So you might want to look at features that have had no usefulness in the past. So we have these various parameters to say, okay, throw in one we haven't tried before. Okay, throw away ones we've already applied and aren't useful, and then try variations on top of things that we've already tried. And so we have various different parameters that you can go in and you can say, okay, I want you to be really selective. So just there's a 75% chance of dropping any features that don't seem to be appearing in the models as useful. So there's various different parameters within here. Any?
Do you work for H2O?
Yeah, I do.
Okay.
Yeah. That's I try not to make it an ad. This is probably the first time in 4 months that I've brought it up, but I just wanted to show because a lot of the fundamental techniques are kind of baked in.
I was wondering how you got your copy, since it's not free.
For academic use, it actually is free. So
Oh,
if you want, you can sign up under an educator license, and there's also various different. You can basically get a trial indefinitely if you just give us an email and say, hey, can I get an extension on a trial license? There's no harm to that. The only time where it's like you really need to splash the money is if you are trying to put something actually in production. That's when we'll kind of hold the trial.
Well, I want to say thank you for showing that, because
nice.
Because we chatted, right? The examples in the book don't necessarily really show you how that transformation of the feature really helped the model. So it was good to see that 0.65 jump to 0.71 on an actual set of data.
Yeah,
I agree.
Yeah.
I saw that the chat was going by. I don't know if I missed anything. Is there anything in there that people want to?
No,
Just
it's
the
us
equal
R
sign.
nerds talking about the arrow assignment operator versus equal sign assignment in Python in virtually every other language.
Okay, so beyond that, any other final questions? If not, we'll take a 10, 15-minute break and then we'll do some project work time. No more questions?
Good.
All right. Then we'll...
Oh, wait. Housekeeping.
We should talk about next week.
Next week. Yeah, we need to talk about next week.
Yeah.
So I'm just going to throw out there that we look at chapters 3 and 4. They both have to do with text. And I think combined it's about another 40 pages, which is how much chapter 2 was basically.
Yeah, that makes sense.
Yeah.
It's like 35 pages.
Yeah. Okay. Does anyone have any requests to go slower than that? I think is the proper way to pose that. No dissenting opinions. Okay. So we'll do chapter 3 and 4 then. That sounds good. Yeah.
All right. Well, great seeing so many people today.
Yeah.
It has been very helpful. Thank you, everyone.
Yeah.
Thanks for everyone showing up. After this, we'll be doing some project time. We'll be looking at the birdsong competition on Kaggle. So just in case anyone wants to stick around, we'll do that in another 10, 15 minutes. But if you're hopping off, have a good rest of your weekend.
All right. Thank you, Ryan. Thank you, Ted. And thank you, everyone. Ciao.
You're welcome.
Ciao.
Thank you.